Hello everyone, welcome to the soft computing lecture series. Today we will be doing the Hopfield Network. So Hopfield Networks were invented by John Hopfield in the year 1982, and this approach is to realize the associative memory. So we already have studied associative memory in the previous lectures. So this is one of the approach to realize this associative memory, and it is an example of auto-associative memory. As we know, in case of associative memory, we have auto-associative as well as hetero-associative. So this is actually a auto-associative memory, a way to realize this auto-associative memory. Then it is considered as a recurrent neural network. It means we are using some feedback. So in this case, some feedback mechanism is used. Therefore, we say it is an example of a recurrent neural network. Then it consists of a single layer. So there is only one layer in this case. We don't have more than one layer. And the same layer is considered as the input as well as the output layer. There is only one layer, and that layer is itself the input as well as the output. Then it is fully connected neural network with symmetric weights. Okay. So it is fully connected and the weights are symmetric. Okay. So fully connected in the sense that the output of neural network is connected back to the inputs. Okay. And it has a symmetric weight. Symmetric weight means what? Weight 1,3 is equal to weight 3,1. Okay. So this is what we say. Then this model is inspired by Maculopet's model. And the state updation can be done in synchronous or asynchronous mode. So synchronous means what? All the weights of the neurons, they are updated at the same time. That is synchronous. And in asynchronous mode, there can be some sequence by which the weights of the respective neurons are updated. Then the weights are updated using the Hebbian learning. As we know, Hebbian learning. So whatever updation, it takes place using this Hebbian rule, and we use a concept as the energy concept is used to ensure that there is a convergence towards a stationary state. So once we give the input, it will just change the weights until the weights become constant. So as soon as the weight do not change, we have reached a stationary state, and energy concept can be used to ensure that it is going to the convergence towards a stationary state. Then Hopfield Networks promoted construction of the first analog VLSI neural chip, so very large scale integration chip. So this was the because of this Hopfield Networks, it was possible to construct the first analog VLSI neural chip. Now this network has found many useful applications in associative memory and various optimization problems. So there are varieties of optimization problems which can be dealt with this Hopfield network. Now there are two types of Hopfield network. One is discrete Hopfield network, other is continuous Hopfield network. Now this is the structure of a discrete Hopfield network. As we can see, this is a neuron Y1, Y2, Y3, Y4. These are the 4 neurons, and this is the input X1, X2, X3, X4. As we see, we are giving the input here, and this output is we can say this is red colored. Now the output, as you can see, it is fully interconnected here. What means that the output, this Y1, is feedback to the input in such a way that the feedback does not goes to itself. See here, this output is red colored, you're getting this red. This goes to Y2, Y3 and Y4. It doesn't goes to Y1. Okay, so this output Y1, so this capital Y1 means the neuron itself, and small y1 is the output. So output of this, it doesn't goes to itself but to all the other neurons. Same way, the output of this neuron, it becomes the feedback for all the other neurons except itself. Same way this for this one and this one. So this is the structure of the Hopfield network. When we give a particular input, we get the output. This output goes again back and it becomes the input, and it continues until the weights are settled down. Okay, so this goes on continuously. So with the inputs and the feedback, the output may change again. Then again maybe it may change again and again until we get a particular value where there is no more change. Then that is the stationary state. So the Hopfields model consists of processing elements with 2 outputs Okay, so there can be two types of outputs. One is inverting, other is non-inverting. Okay, the outputs from each processing element are fed back to input of other processing element, but not to itself. As we saw, the output is given to its feedback to all the other neurons, but not to itself. The connections are found to be resistive, and connection strength over it is represented by Wij. So Wij is the weight. Okay, then excitatory connections use positive outputs, and inhibitory connections use the inverted inputs. So as we saw there, as we see in the first point, one is inverting, other is non-inverting. So the positive outputs, the excitatory connections, they use positive outputs, while inhibitory use the negative outputs. Then connections are excitatory if the output of a processing element is found to be the same as the input. Okay, so whatever output we are getting, when it is fed back to the input, it is same as the output. So that is what we say. So if the output of the processing element is found to be the same as the input, whatever input we are giving, so input is x1, is suppose 1, and the feedback is also 1, then we say that is excitatory. And connections are inhibitory if the input differ from the output of the processing element. So in case if we are giving our input as 1 and we are getting output as 0, so they are different. So in that case the connections are inhibitory. So a connection between the processing element I and j is found to be associated with the weight strength of Wij that we saw. The weight is positive if units 1 and I and j are both on. Okay, so it is, the weight is positive if the units I and j are both are on together. Okay, and the weights are of course symmetric. That is what we saw. The weights Wij are same as Wji. Now the training algorithm for discrete Hopfield network. So training can either be done on the binary data sets or bipolar data sets. So for training on binary data pattern, we have this is the training set from I1 to P. So these are the training set S1 up to N training sets. How do we find the weight matrix? The weight matrix is found by this formula. Wij we can find by using this particular formula. Okay, this is the formula where I is not equal to j. Okay, for I equal to j, the weight is 0. Okay, because there is no feedback from the neuron to itself. So I and j, if they are equal, the weight becomes 0. And then for storing the bipolar pattern, there is a change here in the weight matrix. You can see here that the formula is different and here the formula is different. Okay, so weights have no self connection, though Wii is 0. Then testing algorithm, that was the training. Now we have to test. So the testing algorithm for the discrete network is as follows. The step 1, initialize the weights obtained from the training algorithm. So whatever weights we have got from the training algorithm, we will initialize those weights. When the activations of the net are not converged, then perform the following steps. So perform steps from 3 to 7 for each input vector x. So make the initial activation, we give the inputs of the net equal to the external input x. So what we get is we turn on the inputs, okay, for the various training sets, and we calculate the total input with this. Okay, so this is equal to I xi plus this is the feedback what we are getting. So output yj into wji, this is the feedback. Now we apply the activations such that activations are applied in such a way that yi is 1 if this input is greater than a particular threshold value. It is equal to y if this theta is equal to y in, and is less than theta I, then it is equal to 0. So theta is the threshold. Then last step, now not the last, second last, now feedback the obtained output yi to all the other inputs, other units, thus the activation vectors are updated. And finally test the network for convergence. So this is how the testing is done. Okay, so after training we get the values of the weights, and these weights are now tested so that we get the convergence. Then there is a way to check the convergence, that is by using the energy function. So we use an energy function. So an energy function generally is defined as the function that is bounded and is a non-increasing function of a state of the system. As we know, the energy function is called as a Lyapunov function, and it determines the stability property of discrete Hopfield network. So the state of a system for a neural network is the vector of activations of the units. So this is the energy function. This is the energy function which is Lyapunov function. Then finally the storage capacity on the discrete Hopfield network. So what is the storage capacity of the discrete Hopfield network? It can be found. So the storage capacity is another important factor in case of Hopfield network. It can be found the number of binary patterns that can be stored and recalled in a network with a reasonable accuracy is given by this. So storage capacity is equal to 0.15 times n, where n is the number of neurons in the network. Okay, the storage capacity is this much. So more the number of neurons, more is the storage capacity. It can also be given by this formula. C is given by n divided by 2 log n to the base 2. Okay, so these are the two formulas. So that's how we find the storage capacity of the discrete Hopfield network. So that's all for this particular session. We have studied Hopfield network. Thanks for now watching.